Nico said we are almost on schedule, so continue. But nevertheless, I want to say something about the basic ideas UrbanFlood has been designed. Maybe you don't know, but I am the coordinator, scientific coordinator for UrbanFlood. So UrbanFlood was designed to monitor automatically, without a lot or any human interference, of thousands and thousands of kilometers of dikes. Yeah, the system you deploy, it has been designed that you can say, well, I want to monitor a piece of levee, a piece of dike. We just generate automatically an early warning system. Yeah? We press a button. And the system, you connect it to the internet, and the sensors you connect to the internet, and the system starts learning the behavior of a dike, even if we never have seen it. It's really designed for scale and for low cost, and for and the human intervention you are seeing is more for a collaborative thing. If there is a situation, you can collaborate, you can invest, but the idea is to do as much as possible automatically. The other thing it is designed for is that you could use other modules, other software. There's a kind of a market. You can ask two companies to create software for the UrbanFlood system. Then you have a second opinion for a dike. So there's an open system. Some things are open source, and it is designed for scale. Are there any questions? Because then we keep the time. So there was a small pitch.
Is there going to be a demonstration of such a table?
There is a demonstration of UrbanFlood and the dikes we are monitoring in the hall. Must be visible because there's a large screen. There was another question? Erik.
There seem to be two approaches to data analysis which differ quite a lot in this levy assessment. You're presenting more the artificial intelligence approach, the self-learning approach, and I guess Leo's presentation was more on using past experience and ground mechanical models. And both approaches are claiming to be kind of the future of levee management. I've seen very few combinations of the two. So I'm wondering, okay, which approach will be the winner, and should they not both be combined? I guess, John, do you want to react?
I think maybe it's a good discussion point for the final 15 minutes, actually, but that's the first thing I'd say. Just as a quick reaction, UrbanFlood, of course, does include the stability evaluation, which on a continuous basis, so it's not just a question of artificial intelligence. But I think there is from my point of view, the point that Rob has made about the scope for taking the best of these two approaches is very much, I would agree with you in that.
Okay. I think we continue. My take on this is the following. I feel that I'm not happy. I'm the artificial intelligence, and then I go to a doctor, and then they are doing the finite element analysis. This is how I see that. And you have to do both. The latter one involves much more manual work. Okay.
Different scales.
Different scales. Okay, let's go to the next speaker, Mr. Alexander Pyayt from Siemens. And we know Alexander very well because he's working on the artificial intelligence in UrbanFlood. He does that with Siemens in St. Petersburg. He's doing a PhD research at the University of Amsterdam. And he's going to show what the basic ideas are of the artificial intelligence.
Okay. Good morning, dear colleagues. My presentation is dedicated to application of data-driven methods for flood defense structure analysis. And I will start with very short introduction to our UrbanFlood project. Main task of our Siemens team is detection of anomalies in online stream of measurements gathered from sensors installed into levee, and we interpret anomaly as possible onset of dike collapse. We fully depend on sensor measurements and on quality of available sensor measurements, and I will talk about the problems we have and about the required preprocessing procedures that we apply for available data. And after that, we will talk about the results of anomaly detection. Let's start with UrbanFlood. We are monitoring several levees located in the Netherlands, in Germany, and United Kingdom. But today we will focus mainly on Boston levee. We have two general approaches of anomaly detection. We have one general approach since the start of the project, and we have another transfer function approach that was also developed during this project. The artificial intelligence component is one of the models from this fast response branch of the internal decision support system. If we identify some strange behavior in sensors, we make an alarm, and this alarm is checked by HR Wingford models, and it might be also checked by the virtual dike model developed by University of Amsterdam. But this is a computationally heavy model, and it can be used for online monitoring. And fast response models might be used for real-time dike behavior assessment. In our general approach, at first we group sensors. If we have detected in training set high linear correlation between sensors, we can group this sensor to the same group, and in this case we call it analytical redundancy. We can also make physical redundancy if we can group sensors that measure the same physical parameter or that they have same placement in the neighbor cross sections. After that, we make data preprocessing, and we can use as input for one-side classifiers raw data or extracted features. But this is the general approach. In this presentation, I will talk mainly about another approach, about transfer function. We consider the levee as the transfer function between sensor 1 and sensor 2. And we assume that behavior of levee and also the transfer function is more or less stable in time. And if we have normal behavior of sensor 1, we can identify anomalies in sensor 2 as deviation from the real values from the modeled values. We have selected two transfer functions. These are auto-regression linear model and nonlinear feed-forward neural network. It must be emphasized that for linear model, we should distinguish two different modes. These are simulation mode and prediction mode. In simulation mode, we require only estimations of the output values calculated on previous stages for new estimation of output value. In prediction mode, we require real output values for estimation of every new value. Now about the problems we have with sensor measurements and about the required preprocessing procedures. Usually we have gaps in measurements, there are jitters, measurements are gathered not simultaneously from all sensors. And this requires application of common time grid procedure and application of gap filling procedures. Without these steps, we can't apply most of the data-driven methods. And as the result, we can work already with quite reliable data without gaps and with regularly spaced measurements. In this slide, you can see two sets of measurements from sensor 501 and 506. Red color shows the filled-in gaps. And we know that there was some strange behavior in sensor 506 marked with red color, some kind of sensor fault. And we constructed the transfer function between these two sensors. We used sensor with normal behavior as input, and we tried to simulate as output the sensor with predefined sensor fault. we have split available data set in 3 parts. We generated a training set. We had a test set with definitely normal behavior, and the last part was the test set with abnormal behavior. Here you can see results of linear model application in simulation mode when we do not require the actual real output values for generation of new output values. Here you can see that this type of model provides good alignment with real sensor measurements, so this is presented here. But it also can identify the sensor fault because you can see that deviation presented in this part. So it is different in comparison to other parts of data set. In this slide, I presented results of linear model application in prediction mode. It provides better alignment with real sensor values, but it can't identify the anomaly in data. And the last model, the feed-forward neural network, it provides good alignment with real sensor values, and it can identify the sensor fault. Here you can see the quantitative assessment of the results, and the main idea is that we have constructed the sufficient models, and the both models were linear and nonlinear prediction models. We have identified the available sensor fault using 2 types of models, using this simulation linear model and prediction nonlinear model, and final decision making, which type of model should be used for further Levy analysis depends on expert. This work is supported by UrbanFlood and Siemens, LHC, and many thanks to Eric Peters for providing data. Many thanks for your attention.
So I pick a few seconds to summarize a little bit. If you look through the mathematics, a physicist would see a chain of resistors and capacitors as a dike. And everybody who has had electrotheory in his studies knows that if you have a resistor and a capacitor, there is a phase shift. If you put sinusoidal waves, that's where Jonathan was mentioned. Look, there is phase shift. And if you look at the transfer functions, these are the transfer functions of these simple circuits. And if you do extended theory and you go further and further, then you arrive at Alexander's point, then you get a body of mathematics and a body of technology which is really able to learn how a dike is working. And that's more or less the basics. Are there questions?
Alexander, you mentioned that you can use the raw data just for sensors, but you can also work with features. So
yes.
From Jonathan, we understand that it could be this phase delay,
yes.
shift. What are the other features?
We can extract time frequency features. We can work with FFT spectrum. We can work with wavelet coefficients. So everything that can be used for separation of abnormal and normal behavior.
Rudolf?
Alexander, can you also use this as, let's say, for a benchmark purpose to have one levy compared with another levy in behavior? So if you monitor one levy very, very clearly, and then you use your artificial intelligence to predict how another levy will handle, it's not the subject of your study, I know, but would the usefulness of your study
I think that we can, for example, make analysis of stability of this transfer function, how it can, how often should we adapt this model to changing conditions? Is it really stable? Can we generate it once and forget about producing new transfer functions, or we should regenerate the new transfer function every month, for example? I think we can use it in this case for benchmarking.
Okay, so let me add to this. In principle, what we say, look, the resistor of this dike is so much. Look, the capacity of this dike is so much. If you have another dike, then you get also those two values. And you can compare them to the physical dimensions. Yes? Last question. Press the button.
Thank you. Maybe I'm not completely following, but if I understand correctly, you mimic, or you use the sensor data to train your artificial neural network, let's say, and then afterwards you say, oh, my network is mimicking the sensor's behavior as good enough, but the sensors are there, so what is the advantage of having a neural network when you have sensors in your dike?
I'm not sure that I didn't understand the question.
What is the extra, why do you need a neural network, in fact? Because you have sensors in your dike, so you are monitoring your dike.
Okay.
So you have an additional...
Usually it is not so easy just to generate thresholds, or even by expert, because here we make multidimensional data analysis. If we are analyzing 100 sensors and we generate this neural cloud threshold for 100-dimensional space, I don't think that it is an easy task for an expert. Because we are analyzing all the sensor measurements simultaneously.
If I can just give another response to that. I think the simple answer to that question is that the artificial neural network has got several functionalities to it. One of them is data infill, and the other, which is a useful thing if sensors are going to fail with time, the other functionality is to identify anomalies. So it is quite powerful. It can do more than one thing for you.
We have at the end we have a few minutes to dive deeper in this, because this is one of the discriminating factors we do, and it is of value to understand how it works and why it works, and what another possible answer to the question could be.